Take three. Three types of equilibrium. What a coincidence.
No
It was
kidding.
the universe talking to us.
Yes, three types of equilibrium. We get to answer now, finally, what it actually is.
Yeah. So let's see what we got.
Let's do that.
An equilibrium is simply a reaction that both goes in the forward direction and the reverse at the same time. So there's a special symbol in our chemical notation that we use.
Try this. You and I used to write it like this in school all the time. Right?
Yep. And you could also write it like a double-headed arrow like that. Okay. So equilibriums are reactions that have two directions. And that's the symbol that tells you whatever reaction you're looking at on paper is an equilibrium, or if it's just a one direction.
Right. So there's a forward reaction and a reverse.
And the key about it is that it's happening at the same time.
Right. And so notice the rates of the two reactions must be equal.
Mm-hmm.
Not only does it look like an equal sign, but it's the rates that are equal. You've heard us say it in class a lot. I know I've been really stressing that.
Right.
Because it's not the concentrations that are equal. You know they're going to try and catch us on that question.
For sure. Let's see what else we got here. There you said it. The concentrations must be constant. So it's kind of like when one particle breaks apart, another particle will form to take its place.
Correct.
It's kind of like there's only a certain number of spots on the team. Somebody gets kicked off, somebody else picks up that spot.
Right. Somebody comes off the bench, somebody goes on the bench.
Right, exactly. There's only that many players on the field, so that it's an equilibrium number. There's more players sitting on the bench than there are on the field sometimes.
Right.
But there's always, if there's a switch, it's a substitution. So it's just an even swap.
Right.
One goes in, one
you
comes
can
out.
make a playoff analogy there, because at playoffs you get to call up more people. So all of a sudden you got a lot more people on the roster,
but not that many on the field. I mean, in basketball, there's only 5 guys on the court at any one time, but there might be 12 others sitting on the bench.
Right.
And that's where we say concentrations must be constant, and if somebody comes out, somebody goes in. So it's a rate
So the
thing.
number of the players on the field is always the same.
Mm-hmm.
Number of the players on the bench is always the same, even though they're different numbers. So they don't have to equal.
Right.
They just have to stay constant.
The rate's equal. It's not like you can put 2 guys in and only take 1 guy out.
Right. The rate's got to be equal.
Because the
guys
rate
in, you got to
would be
take
equal.
2 guys out.
Exactly. It would
There
be
we
called
go.
legal formation or something.
Oh, there you
Who knows?
Okay.
So they're dynamic equilibriums.
There we go.
And so there's a great animation here where we've got A2 and B2. They collide, collision theory. They cause a reaction, and they go in the forward reaction to make 2 ABs.
Yeah, I mean, it's moving a little bit fast, and it's tough to see, but if you really focus, you'll see AA goes over, BB goes over, but whenever that happens, 2 ABs come over and form AABB. So it's a loop.
And if you want to use some previous vocabulary, it's both a synthesis and a decomposition at the same time.
Simultaneous is the key there.
Mm-hmm.
And here, this picture helps show us that.
Yeah.
A little bit slower so we can see.
I'll go and then trace out the route.
So if a cyanide ion and an iron ion hook up, they form this iron cyanide complex, and that's happening. And so now 2 reactants just formed a product. Well, if that's going to happen, every single time that happens during equilibrium, a product must break apart and form a cyanide ion and an iron ion. And that happens at the exact same time. So when we say that the concentrations are constant during an equilibrium, it looks like nothing's happening. But the trick is that there really is something happening. You just can't see it, because every time an iron cyanide is formed, an iron cyanide is broken up, and there's always the same number of each, no color change, nothing like that we see happening. But this equilibrium is consistent.
And the 4 I wrote on the reactant side was for the 4 ions that were present. And the 3 I wrote on the product side was for the 3 products that were reacted. So you can see the concentrations are not the same. It's not 4 and 4 and 3 and 3. Those are different.
The concentrations stay
constant. Right. So for every one that forms, one breaks apart. One that forms, one breaks apart. That's what we're trying to show you with the equilibrium.
And that's why the part that's equal is the rate. Every one that goes forward, one has to go back. If 2 go forward, 2 have to go back. So the rate's got to be equal, not the concentrations. That's what we're trying to hammer home there.
So a chemical equilibrium is what we've shown you so far. So chemical reactions forming forward and reverse in the same time, in the same moment, in the same instance. The hard part about this is, since it's happening forward and reverse at the same time, it appears to the naked eye like nothing's going on.
Yeah, you can't see it happening necessarily, because the color change would usually be dependent on the concentration. And if that's not changing, then it doesn't look like anything.
Exactly. So that's what's tough about chemical equilibriums. Right. Physical equilibriums are a little bit simpler.
Right. So here we got, on the far left-hand side, that initial state, you have some liquid in a sealed container with air on top. Now, what's going to happen when it comes into equilibrium? Some liquid molecules are going to evaporate into that air, into that space, until enough have filled up that it stops. Now, everyone that goes into the gas phase, one in the gas phase has got to come back down to the liquid phase, and now it starts a one-for-one cycle in this closed system. So that's what we call a physical equilibrium. It's more of a phase equilibrium, if you will, leading to the next one. And watch, we're going to take phase, cross him out, and write solution. Make sure you write that solution, because that's different. A solution equilibrium is different than a phase equilibrium.
Right.
This is where we have this solution of lead chromate. Got that right?
Yep.
And I've saturated the solution with lead chromate. So that solvent up top has got as much lead chromate in there as it can possibly have. But there's a little extra powder on the bottom, the crystal, if you will. So now every time a crystal goes into solution and dissociates, some ions have to reform and come back out of solution and form crystals. And that's going to happen continuously, and it'll look like nothing's happening.
It is always going to be a saturated solution above the crystal.
Yeah, that's a matter.
You've got precipitate sitting on the bottom. What it means is that the liquid above it has absorbed, dissolved as much of the precipitate as it can. And you won't notice it quite right away. We can see it changing over time slowly in some of my potassium nitrate bottles, my concentrated ones. The crystals that I originally grew were really sharp. Now, 6 months later, they're not so much anymore.
Right, but we'd have to time lapse that to have any kind of be able to see it. You won't be able to see it. So, but that's what we need to know about equilibriums. Now, to maintain them, basically, we need to have a reversible reaction. Right. So there has to be a forward and a reverse, or it's not an equilibrium. Otherwise, it's a one-way street. We've seen one-way streets in the city. They happen. All right. And then most times we have to have the system closed, like that one we have with the liquid there, because we can't have the product escaping, because then it can't go in the reverse direction.
Exactly. Like if I have A and B and they come together to make C, if C leaves,
then it ain't going to be around to form A and B.
It's not forced to break apart to form A and B again. It might leave and form A and B somewhere else, but if it's not in the closed system, the dynamic equilibrium cannot be maintained.
Right. It becomes a one-way street.
Exactly. So most reactions are in fact reversible. It's just that the products escape, so we never force them to go backwards.
Right. Especially when the products are gas versus solid or liquid, then it's
Really
easier
easy
to hold on to solids and liquids, not so much gases. I think that's it for this video.
I do believe so.
Yeah, brace for the long one. It's next.
Thanks.
Bye.
I click the button and it'll stop.
I'm letting you click that button.
Button click.